Hello, this is your practice exam for statistics for chapter 3 in my class. I would like to show you how to find the practice chapter 3 exam. So when you log into Canvas, you'll go to modules and you'll just go down to chapter 3. And at the bottom is your practice exam. So what I'm about to show you is going to be the practice exam that you are going to hopefully have printed out and are following along with me as we're doing this, or if not printed out, at least on a screen somewhere. All right, so we're going to start here with number 1. And we have some precipitation in August for 20 different US cities, and they want to find the mean monthly precipitation. Well, what you would normally do is you would take a few minutes and put all of that information into your calculator. And I've already put the information into my calculator. So you don't have to watch me do that. So my list one, this is the same numbers that you have there. And to find the mean, what I'm going to do, as I quit out of that, is I'm going to go to stat, and I want to calculate using one variable statistics or one var stats. And the information I want to use is in list 1. I'm actually going to be using, I think, 5 lists for this review. I'm going to go down to calculate. And there's my mean. So again, using your calculator, it will do it for you. What you would need to do if you didn't want to use the calculator is you would add up all of those and then divide by the number was it 40 of them or whatever it was. So the answer is 2.94. Again, all I did was copy down that there. That's my X bar. So for number 2, they're asking for the median as we're looking at this. Now, to find the median by hand, you have to put all of this data into order, the proper order. And you can see they're definitely not in order. It would start with the -14, then the -9, and so on. Once again, I've already loaded all this into my calculator, so you don't have to watch me do it. And I will show you a handy dandy trick. So quit out of that. I'm going to go to stat, and I'm going to show you that list 2 is exactly that list that you just saw, that we want to find the median. So I'm going to use list 2 now. And I'm going to go back to stat, calculate one variable stats. I'm going to change that to list 2. Let me show you how to do that. It's L2 is right above my 2 here. So I'm going to hit second and L2, and that changed it to L2 for me. I go down to calculate, and remember, I'm looking for the median. Good news is if I scroll down, the median's right there. It's 4. Now the median, what that means is if I rewrote everything in order, all the numbers in order from smallest to biggest, then all I would need to do is just find that middle number. Remember, if there's 2 middle numbers, you find the mean of those 2 middle numbers as you do it. So for number 2, this was the answer there. For number 2, the median, pardon me, is 4. Easy enough. Number 3 is the mode. Now the mode is the most frequently listed number. And in this case, if we were to look at this, I see 5.0, 5.0, 5.0 3 times. I also see 6.2, 6.2, and 6.2 3 times. And none of the other ones are that frequent. So in this case, this is what we call bimodal. There are 2 of them. And switching back real quick. That means that for number 3, 5.0 and 6.2 are our 2 modes. Back to 4. All right, so we're looking for the mean of a frequency distribution table. This one's going to take a little bit of time. So what I need to do first is find the midpoint of each of these speeds. And the way you do that is you take the 39 plus the 30 and divide by 2, and that'll give you the midpoint. Let me show you what I mean. So for number 4, the midpoints, which we'll call X, versus the frequency, this is what we'll call F. So the midpoint for the first one is going to be the 39 plus 30 divided by 2. So meaning we're going to make the midpoint of this class represent that class. Next up is 49 plus 40 divided by 2 is going to give me 44.5. Next up for the third class, it's going to be 54.5. It's going to be 64.5. And lastly is 74.5. And once again, the frequencies are the same, 5, 10, 18. 18, 50, 17, and 10. Now we need 2 pieces of information to do this. So let's switch colors a little bit. So we're going to be adding up. Remember, that's a capital Greek letter S called a sigma. I'm adding up F times X, and we're dividing that by the total frequency. Now, summation of F is going to be me adding these up. So let's just add those up real quick, and that'll be my denominator. So 5 plus 18 plus 50 plus 17 plus 10 gives us a nice even 100. So this is going to give us this times this. That's what this means. So 34.5 times 5, 72.5 plus 44.5 times 18, 801 plus 54.5 times 50, 2725 plus 64.5 times 17. And lastly, 74.5 times 10, which we could do in our head, just move the decimal. 745. All divided by 100. So let's add those up. I already have the 745 here. So 172.5 plus 801 plus 2725 plus 1096.5 divided by 100. So our mean is about 47.95, and these are miles per hour. Not too bad. A little crazy, but not too crazy. Let's move on up for number 5. Excuse me. Number 5. Here we are looking for the standard deviation. And once again, I've already put these values into the calculator. First one would be 14.7. Let me show you. There, 14.7. I put that into list 3. And to find the standard deviation, this is a sample standard deviation. What we're going to do, mark this up. Number 5 is I'm going to kick out of this, remembering that we are in list 3 now. Once again, I'm in L3. So I'm going to go stat, calculate, one variable statistics again. And I'm going to change that to L3. Again, the way I do that is it's above the 3, L3. So second L3. You can see it changed it to the L3. Calculate. And my standard deviation for a sample is the SX. So, and how do they ask us to round this off? One more decimal place than the original data. So there was 1 decimal place, so we're going to round it off to 2 because they want 1 more than that. So the sample standard deviation is right here, 11.26. Again, you're using one variable statistics. Get a lot of good stuff out of that. All right, next up, number 6. All right, range rule of thumb to estimate the standard deviation. Well, standard rule of thumb says we're going to take the largest value, which in this case is the 6.2, minus the smallest value, which in this case is the 5.4. And then I'm going to divide it by 4. That's the rule. So let's switch back and do that. All right, once again, the largest. So this is our standard deviation. This is an approximation. The largest, which is the 6.2, minus the smallest, which is the 5.4, divided by 4. (6.2) minus 5.4 equals divided by 4. 1, 2. And a range rule of thumb. This is of heights of people. So for our next problem, for number 7, we're going to use something called the empirical rule to figure this out. And I have a little table from my notes. I apologize, they're already written on. Sure you're on the right screen, we are. And basically it says when I have the mean, if I go 1 standard deviation away in both directions, that will capture 68% of the data, of the information. If I go 2 standard deviations out, that means I can capture 95% of the data. You can see most of the data is going to be here. If I go 3 standard deviations out, which we normally don't do, then that would capture 99.7% of the information. We'll learn where those numbers come from later in the semester. So just keeping that in mind for our number 7. So we're going to use the empirical rule to solve this problem. At one college, GPAs are normally distributed with a mean of 3 and a standard deviation of 0.6. What percentage of students at the college have a GPA between 2.4 and 3.6? So let's go back. Number 7 here. And I'm just going to draw a little deal here. They said the mean is 3. And the standard deviation, so the mean is 3 and the standard deviation is 0.6. So if I want to go 1 standard deviation away in both directions, then this is going to be 2.4. and this is going to be 3.6. And you can see in the problem, that's how far they want us to go. So this is each one standard deviation. So this is minus a standard deviation. And this is plus a standard deviation from the mean being 3. So you can see when we go one standard deviation away, what percent are we getting? 68%. Again, you don't know where that number came from right now, but we will eventually. So the answer is 68%. And if I remember right, number 8 was very similar. I mean, meaning we can use the empirical rule again. All right, so number 8. Is here. So the amount of Jen's monthly phone bill is normally distributed with a mean of 55 and a standard deviation of 12. What percentage of her phone bills are between 19 and 91? So let's go back. See what to do about this. This is number 8. And I'm going to do the same idea that I did before. Draw it out a little bit bigger this time. And the mean is 55. And the standard deviation is 12. So I'm going to go 55 plus 12. Plus 12. I'm going to go 3 out just to see. Plus 12. Now we got 91. Now I'm going to go 55 minus 12. Minus 12. Minus 12. 19. And you can see from the mean, 55 in this case, we are going 1 standard deviation away, 2 standard deviations away, and 3 standard deviations away. Three standard deviations away. And if I look back at my empirical rule, if I'm going 3 standard deviations away, excuse me, I'm all the way out here. And that is capturing 99.7%. So my answer for number 8, 99.7%. Meaning nearly 100% of her phone bills are between $19 and $91. There might be some special month when, for whatever reason, this is very old. This isn't dealing with cell phones. This is back in the day when you had long distance and there were different rates for different types of calls and things like that. So kind of forgive the how old this is. But we're going to move on to number 9. And let me show it to you. The mean height of a basketball team is 6 feet with a standard deviation of 0.2. The team center is 6.9 feet tall. Find the center's Z-score, and is his score unusual? Now remember, unusual means if we're more than 2 standard deviations away. Let's check it out. And remember, Z-score is the number of standard deviations we are away from the mean. Number 9. Well, his Z-score, the formula for that is you take the data point, the single data point minus the mean, and you divide that by the standard deviation. And in this case, he is 6.9, pardon me, that's not 6'9", that's different. 6.9 minus the mean, which was 6 feet, divided by the standard deviation, which was 0.2. Let's see what we get. .5. So there is his Z-score And his z-score is definitely bigger than 2. And anything bigger than 2 or less than -2 is considered unusual. Doesn't mean the person is unusual. It just means his height is unusual relative to the rest of the team. Next up, number 10. Speed that up a little bit. Another problem about z-scores. All right. Excuse me. Which is better, a score of 92 on a test with a mean of 71, standard deviation of 15, or a score of 688 on a test with a mean of 493 and a standard deviation of 150? We're gonna have to calculate two z-scores, and the larger z-score means that they are further away from the mean, which means they did better. So we're looking which of these two z-scores are gonna give us a larger z-score. That's gonna be the person who did better on this particular test. These two tests, I should say. All right, so our first z-score, I'll call it z sub 1, is going to be a score of 92 minus 71, which is the mean, divided by the standard deviation, which is 15. .4. Now, z sub 2 is going to give us the 688 minus the 493 divided by 150. So 688 minus 493 divided by 150. So which is a better score, a 92 for this test or a 688 for this test? 92 is better in this case. Is a better score. So changing it to a z-score is nice because what that does is that converts any two things that you want to compare, and you can see which one is better or not. Next up, we have percentile. Students often struggle with percentile, and that's certainly understandable. In fact, I think we have 3 of them that are, yep, and then we'll do a box plot, then we're done. All right, so number 11, this data set here is not in order, and we want to know what the percentile is for the value 42. What I've done is I have already put these numbers into my calculator to save us some time, and so I want to show you. To do this, the numbers need to be in order. So let me show you. Here I'm in list 4. And you can see so I'm in list 5, pardon me. And what I need to do is put list 5 in order. So I'm going to do this stat, and I'm going to do it sort in ascending order. And I'm in list 5, which is above 5 here. I5, you can see it, L5. And now I can go back into list 5. And you can see it's now in order. Yay. So I'm going to actually write these out. This is number 11. And we go up. And I'm going to write these out in the order. So 6, 2 12s, 3 18s, 24, 30, 36, 42, 54, 54, 54, 54, 66. Blue. That's it. Okay. So this particular one wants to know this location here. It basically wants to know what the percentile is. And what that means is we want to know what percent of information is below this location, not including this location. So here's how this works. I'm going to take the number, by the way, there's a total of 15 pieces of data. And how many are below my 42? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 out of the 15, pardon me. 9 out of the 15. And I need to change that into a percent. So let's see what we get. 9 divided by 15 times 100. So here's the answer, 60. And let me interpret this. This means that P sub 60 is 42. Kind of cool. Moving on to number 12. Now we're going the other way. We want to find P sub 16. Let me go back and show you. We want to find P sub 16 based on this data here. Now, luckily, I didn't have to put this in my calculator because it's already in order. And they tell us that there's 30 newborn. So what I need to do is find 16% of the 30, and that's going to give me a location. So real quick, let me show you the calculator. So I need to find 16% times the number of data pieces, which in this case is 30. So 16%, 0.16, that's 0.16 there, times 30. This gives me a location. 4.8 location. Now, of course, we don't have a 0.8. So what we're always going to do in this case is we're always going to round up. So we're going to go find the 5th location. And I'm going to find that here. So 1, 2, 3, 4, 5. There it is. 6.1. That is my answer. The answer is going to be 6.1. So we could rewrite it as P sub 16 equals 6.1. Meaning at this data location, for sure, there's going to be 16% below it of the data. Now, notice this one came out to be a decimal. This next one is not, and we're going to have to do something a little bit differently with that. So let's move on to 13. Number 13, we want P sub 85, meaning I want to find the location that will guarantee 85% of the data will be below it. There are 40 here total. And so basically, I need to know the location that is going to give me, of these 40 students, 85% of the data below it. So I need to find 85% of 40. So let's do that. So I need to find 85% of 40. So 0.85 times 40. Now notice this one is not a decimal. The previous one was. And we had to round it up. This is going to cause a problem. because at the 34th location is not going to give me below it 85%. So let me show you how this works. So this first one here is 1 through 10, 11 through 20, 21 through 30, and 31 through 40. So this is 31 here, 32, 33, and 34th. Here's our 34th location, the 85. Now, by the way, this 85 has nothing to do with this 85 as far as they just happen to be the same number in this case. But at this location, below it is not going to guarantee 85% of the data. So what I'm going to have to do is take the 34th and the 35th position and find the mean between the two of them. That's the 85 and the 89. And then that will be. This only happens, we're only going to do this weird thing when we do the calculation, it goes to an exact number opposed to a decimal. So the 34th has the value 85. And the 35th location has the value 89. So to find what the data value that we want, we're going to find the mean. So 85 plus 89 divided by 2 is 87. Even though 87 is not a piece of data in our particular set here, we say that P sub 85 in this data set is 87. All right, we are to our last problem. So we're going to construct a modified box plot for this data. And I'm going to use this sheet. There we go. This is number 14. And this data, we of course need to put into the calculator. That, edit, oop, too far. It looks like I didn't put the data in, but luckily for you, I can pause it and you won't even notice. And magically, you can see the data in my calculator, which is in list 6 now. What I'm going to do for this data to construct it is I'm going to do a 5-number summary. So I'm going to have the minimum value, Q sub 1, the median, Q sub 3, and the maximum value. Now, remember, I'm in list 6 here. So I'm going to run one var stats again. This time on list 6, which is above my number 6. So second L6. And we're going to calculate it. And very, very nicely, the calculator gives us all of the information that we need, which is really cool. So the minimum value that we hit was 1.7. Q1 is 2.5. Median is 2.7. Q3 is 3, and then 4.2. Now they want a modified box plot, so we are going to look for outliers. So first thing I'm going to need is my interquartile range, or the IQR, which is Q sub 3 minus Q sub 1. In our case, That is 3 minus 2.5, and I can see that that's just 0.5. So now we're going to look for outliers by finding our lower fence and our upper fence. So our lower fence, or LF, is q sub 1 minus 1.5 times the IQR, which in this case is 2.5 minus 1.5 times 0.5. That is our lower fence. Our upper fence is q sub 3 plus 1.5 times the IQR, which in this case is 3 plus 1.5 times 0.5. 3.75. Now we're going to look for outliers. So if there's any data values that are smaller than 1.75, that's going to be an outlier. We're going to throw it out. If there are any data values that are bigger than 3.75, we're going to throw it out. Let's go back to the data. So here we are with our data. And I can see 1.7 is below my lower fence, which is 1.75. It's a little bit bigger. So 1.7 is an outlier. The next one up is 2.0. That's bigger than 1.75. So it's above our lower fence. So let's go to the other side. Anything bigger than 3.75 is an outlier. And I can see right here, 4.2, that's an outlier. The next one down is 3.6. That's below 3.75. So we're good to go. So our conclusion So 1.7 and 4.2 are outliers. Well, we're going to do a box whisker plot, or box plot they call them now. Let's make it big. 1, 2, 3, 4, 5. All right. First of all, we're going to label our outliers. 1.7 is about there. We put an asterisk. 4.2 is going to be here. I'm going to put an asterisk. I'm now going to put my interquartile in there. So 2.5 is about here. 2.7 is there, and 3 is there. So I'm going to do this. And I'm going to draw our box. Now we need the whiskers. I can't go all the way out to 1.7. Now, if this was a non-modified one, then I would go out to the outliers, but it's not. So what I'm going to do is I'm going to go back to the data. What is the smallest data value that I have left? What is the largest data that I have left? That's not an outlier. 1.7 was out, so that means my lower is going to be 2.0, and that one's out. So that means my upper is going to be 3.6. So my lower is going to be the 2, and my upper is going to be the 3.6. And here are my whiskers. Modify box plot with the outliers. I hope that helped. Thanks.